Greetings, ladies and gentlemen. I'm Sarvagya Bhatnagar, accompanied by Jonathan Liu and Glenn Chong from NTU's Biomedical Engineering Society. Today, we are thrilled to present an innovative AI-driven solution tailored for monitoring the disease progression of type 2 diabetes mellitus and enhancing patient adherence. Type 2 diabetes is a chronic condition characterized by insulin resistance, resulting in elevated blood sugar levels. Monitoring this condition involves assessing average blood glucose levels over 3 months, along with fasting blood sugar tests and oral glucose tolerance tests. Complications such as heart disease, kidney failure, and nerve damage can arise, significantly impacting patients' lives. Management includes lifestyle modifications, blood sugar monitoring, and medications like metformin, necessitating regular checkups to adjust treatment and prevent complications. Disease progression mandates frequent physician checkups every 3 to 4 months, involving the use of short-acting and long-acting insulin based on carbohydrate intake and body weight. Continuous blood glucose monitoring is essential but invasive and prone to forgetfulness, particularly challenging for elderly patients. Similarly, Singapore, a culturally diverse nation, grapples with a high prevalence of type 2 diabetes exacerbated by an aging population, despite significant government investment in combating the disease. Current management methods lack precision and may lead to dangerous blood sugar fluctuations. Daily check-ins with physicians are beneficial but taxing, especially for elderly patients. Non-adherence to self-injections can result in severe complications, emphasizing the need for individualized, accurate, and personalized treatments. Our solution comprises an AI model for precise insulin dose recommendations and a device employing behavioral medicine principles to enhance patient adherence. The AI model aligns with precision medicine, optimizing insulin doses throughout the day more effectively than current methods. The device leverages the habit loops to cultivate regular usage habits, utilizing continuous glucose monitoring and timely notifications for insulin administration. A user-friendly interface with chatbot support facilitates ease of use, while maintenance of glycemic levels rewards consistent utilization of our solution, improving the overall adherence rates and satisfaction.
Our predictive AI model for type 2 diabetes management helps patients by informing them when and how much insulin to inject based on their blood glucose levels. It was created and trained using retrospective patient data, continuously growing and improving through the ongoing data collection process. The model is part of an ecosystem connected to a device and an app offering constant blood glucose and biomarker monitoring and timely injection notifications. This enhances patient adherence, leading to better glycemic management and overall health outcomes, and a robust ecosystem that promotes consistent patient adherence. And I present to you our AI model, the FRAG VLLM. Okay, it might look like a lot to digest, but don't worry, I'll break it down over the next few slides. First of all, Federated learning is a decentralized model to analyze blood glucose profiles. It selects relevant data to train the model while ensuring data privacy and robustness. By collaborating without sharing sensitive data, it allows local updates on individual devices and model updates on a central server, enhancing security and efficiency. Retrieval Augmented Generation, or RAG, enhances information retrieval from large sources. This method is safe and accurate, improving data accuracy and relevance. It doesn't require a central data center, which keeps costs down while maintaining data secure and efficient. Now finally, the Very Large Language Model, or the VLLM, is an advanced natural language processor (NLP) model containing millions of patient data points, with blood glucose levels recorded every 5 minutes. It is trained like a ChatGPT on patient blood glucose levels instead of billions of Wikipedia pages, ensuring accuracy and relevance for diabetes management. So overall, the patient-level FRAG VLLM involves regular checkups and biodata collection. The LLM monitors data and alerts patients when the blood glucose level drops below the baseline, advising them on how much and when to inject the insulin. This ensures timely medication, smoothly returning blood glucose level to the normal. At the FRAG VLLM AI level, the patient's blood glucose level is analyzed. If the blood glucose level is above or below that baseline, the AI will proceed. Otherwise, it does nothing. So using federated learning, similar patient biodata are selected. And this AI suggests how much to inject, when and why, based on this biodata comparison to similar patient profiles, which has never been done before. Our AI MVM for personalized treatment reduces manpower involvement and caregiver burden, leading to better adherence without the sharp dips below the threshold, ensuring neither too much or too little of that dip. This using precision medicine and personalized biodata means that better adherence to each patient's needs. This approach enhances research and knowledge discovery, predicting potential disease risks using federated learning to prepare for new patient activities, which has never done before. RAG ensures patient data protection, and the model decreases costs, enables caregivers to focus more on care, and enhances patient education and management. It supports further data analysis and learning, preparing the model for more scenarios with the least amount of data present.
Our FRAG VLLM model will be coupled with an innovative precision device that utilizes novel technology, further revolutionizing diabetes care and management. Our device is designed with two overarching goals in mind, targeting multiple biomarkers with novel approaches for better biomarker monitoring and non-invasive insulin delivery methods to ease patient burden. Now, you may be wondering, what did we do to achieve this? Well, follow me and I will give an in-depth explanation into our creation. The biomarkers that we have selected for monitoring include the usual blood glucose levels and new proposed biomarker, glycated hemoglobin or HbA1c. Blood glucose levels are already used in day-to-day monitoring, albeit invasively, in continuous glucose monitors and hence will provide a clinically approved standard monitoring parameter. Next, glycated hemoglobin is formed when glucose is condensed on the N-terminus amino groups of the HbA beta chains. Measured every 3 to 4 months, it is mainly used for the long-term monitoring of glucose control resistance and potential disease complications. By being able to continuously monitor HbA1c, it can not only give us a more accurate representation of the patient's blood glucose levels, but also a more accurate extrapolation of the disease progression, allowing physicians to more accurately and proactively tweak the patient's treatment plan. With blood glucose and HbA1c having a spectrophotometer absorption peak of 900 to 1700 nanometers and 545 and 579 nanometers respectively, our measurement technology is based on spectrophotometry, the quantitative measurement technique based on the principle that every compound absorbs a specific wavelength of light. This provides us with new, non-invasive means of biomarker monitoring. Our non-invasive infusion technology is based on the MIT studies done on the single transducer dual frequency ultrasound generation, utilizing both low and high frequency oscillating ultrasound waves. Microbubbles are rapidly formed and collapse in the interstitial fluid. The collapse of the microbubbles create microjets and intense local shock waves. These shock waves temporarily and harmlessly disrupt the outermost layer of the skin, creating microchannels that increases the permeability of the skin to the insulin. Furthermore, these microjets allow for the rapid diffusion of insulin over a wider area. With these groundbreaking technologies in place, we are proud to present our new non-invasive precision device. Next, we move on to how we plan to achieve our project. The first 2 years will be used to develop our VLLM model, which includes collecting datasets for training and canvassing for funding sources. This is then followed by publication of our model in year 3, which will then be continued by gathering patient feedback, collaborating with various institutes to refine and implement our solution. Next, we will commence the device development from year 3 to 5 after pitching the designs to institutions and collecting additional grants. With clinical trials planned in year 5 and 6, along with regulation licensing from year 6 to 8, we plan to commercialize our product from year 8 onwards. Our financial plan includes collecting grants from both research collaborators such as NHIC Singapore, Alice Center Singapore, A-Star Singapore, and AI Singapore, and industrial collaborators such as Medtronic and Ascensia. With this in mind, this would be our final timeline for the development of our solution. The impact of our solution will be evaluated on how well both patient-level and system-level barriers are breached, based on the number of instances where patients' blood glucose levels are found out of the threshold range for the patient's level barriers, and the frequency of checkups and overall cost to the patients for the system-level barriers. Overall, we believe that through federated learning, coupled with high sustainability and close working relations with government institutions, this solution may potentially be the future of type 2 diabetes mellitus management and care. Thank you.